The sun is our most constant companion, yet for decades, its behavior contradicted our models of how a star should function. In the 1960s, chemist Ray Davis attempted to prove the sun's nuclear fusion engine existed by counting neutrinos, subatomic particles produced as a byproduct of hydrogen fusion. This chart shows the discrepancy that stalled solar physics for a generation. Davis found only 1/3 of the predicted neutrino flux. Either the sun's core was cooling, or our understanding of particle physics was missing a critical component. There was also a temperature contradiction. The solar surface is roughly 5,500 degrees Celsius, but as you move outward into the atmosphere, shown here, the corona, the temperature rises to 1.6 million degrees. Heat was moving from a cool surface to a hot atmosphere, seemingly in reverse. To reconcile these gaps, researchers had to look past the visible spectrum and build sensors capable of detecting the invisible. Scientists built massive detectors like this one, buried deep underground to block out cosmic interference, to catch the missing neutrinos in a tank of ultra-pure water. This diagram illustrates the solution to the missing neutrinos. They weren't gone, they were oscillating. As they traveled from the sun to Earth, they cycled through 3 different states, effectively hiding from earlier experiments. To confirm the exact source of the sun's energy, the Borexino experiment used an ultra-pure liquid scintillator to detect the lowest energy neutrinos produced by the solar core. This model shows the fusion processes Borexino mapped, the dominant proton-proton chain and the rarer CNO cycle. Measuring these CNO neutrinos revealed the exact concentration of carbon, nitrogen, and oxygen in the core, resolving the solar metallicity puzzle. By isolating these ghost particles, we confirm the sun's fusion engine operates exactly as predicted, providing a definitive map of our star's power source. Solving the atmospheric paradox required a different approach. In 1942, Alfvén proposed that magnetic waves were responsible for heating the corona, but he lacked the technology to see them. The Daniel K. Inouye Solar Telescope was designed specifically to find those waves. Its 4-meter mirror provides the resolution necessary to track plasma movements in the sun's outer layers. The telescope's cryo-NIRSP instrument followed superheated iron ions, measuring spectroscopic shifts that occurred too quickly for previous instruments to capture. Researchers finally observed torsional Alfvén waves. Instead of swaying back and forth, the magnetic field lines were twisting. This twisting motion acts as a physical pump, transferring magnetic energy directly into the corona, explaining its million-degree temperatures. The mystery of the corona was solved by looking past the glowing plasma and tracking the magnetic vibrations rippling through it. The superheated corona continuously sheds its outer layers into space, forming the solar wind that fills the entire solar system. During periods of high activity, the sun hurls billions of tons of magnetized plasma toward Earth in events known as coronal mass ejections. To protect our infrastructure, NOAA utilizes the WSA-Enlil heliospheric model, which integrates our data on solar magnetic flux and coronal temperature. This model tracks the propagation of these magnetic storms as they travel toward Earth, mapping the physical path they take through the inner solar system. This forecasting provides the lead time necessary to safeguard GPS satellites, our communication networks, and power grids from magnetic interference. Solving these ancient paradoxes has transformed our ability to monitor the solar environment and predict the magnetic storms heading our way.